Welcome back. One way to acknowledge that there is correlation in the data is to perform a transformation which will decorrelate them. Then the transfer coefficients are uncorrelated, and each of them conveys unique information about the image. Some of them convey significant amount of information, as measured, for example, by their variance or their contribution to the total energy of the image, while others have contributions close to zero. The latter ones can therefore be ignored or heavily quantized when compression is performed. This is the topic of this segment. We first discussed the decomposition of an image using an orthonormal basis. This is a straightforward extension of such a decomposition when we deal with vectors. Now, if we place the requirement that the resulting coefficients of this decomposition are uncorrelated, then we end up with the Karhunen-Loew transformation. This is the optimal transformation for our purposes, but it has the major disadvantage that its bases are not fixed, but they are functions of the autocorrelation of the image. That is, they're different for each image we are interested in encoding. This makes the KL transform impractical, and instead the transform of choice is the discrete cosine transform, or DCT. We show with a simple experiment the usefulness of the decorrelating transforms, such as the DCT, in deciding which part of the data to keep and which to discard. So, let us proceed with this interesting material. We cover in this segment transform-based coding. This is a useful and popular approach which has been adopted by most, if not all, image and video compression standards. We show here the three building blocks of any encoder. As mentioned multiple times, data are compressible because they're correlated. With predictive approaches, such as DPCM, this correlation is taken into account directly. For example, we are solving for the linear prediction coefficients by utilizing values of the autocorrelation function of an image. With transform-based coding, we take the transformation of the data of an image or an image block. The objective is to obtain transform coefficients which ideally are statistically independent. So the contribution of each coefficient towards the original image is independent from the contribution of the remaining coefficients. We then look at the relative importance or contribution of these coefficients towards the original image. For those coefficients that contribute more, we treat them gently. We quantize them with a fine quantizer. And for those coefficients that contribute considerably less, they are quantized coarsely or they're discarded. So this is the purpose of the quantizer here. We say that the quantizer has a spectral shape. It's uniform, but the step varies depending on the frequency of each coefficient. The quantized transform coefficients here are entropy encoded using any of the techniques we covered last week, such as Huffman and arithmetic coding. It is therefore this bit stream that is sent to the decoder. Now, the decoder is undoing the steps of the encoder. So the binary bit stream is entropy decoded, and here the symbols, which are the quantized transfer coefficients, are inverse quantized. This is actually a misnomer because quantization is an irreversible process. What it's referring to is to the fact that when quantization is performed, we divide the number, the value of the coefficient, by the step of the uniform quantizer, and what is sent to the decoder is the quotient of this division. Therefore, inverse quantization or dequantization refers to the fact that this quotient is multiplied back by the step of the uniform quantizer to obtain the actual value of the coefficient. And then finally, we perform inverse transformation to obtain the reconstructed image block. So let's look first at the characteristics of such transformations. So what are some of the important characteristics of such transformations? They should decorrelate the data. So in principle, the transform coefficient should be statistically independent. At the same time, they should perform energy compaction, which means a small number of such coefficients should represent the majority of the energy in an image. The bases that form such transformations should be independent of the image we try to encode. Otherwise, these bases should need to be transmitted to the decoder to perform the decoding. And finally, as always may be, we would like to have fast implementation of such transforms, since they're clearly part of both the encoder and the decoder. We show here a comparison of such transformations. What is shown here is the log variance of each coefficient in the vertical axis and the coefficient number in the horizontal axis. So the image is broken into sub-images, and then for each sub-image the transformation is found. So therefore we have, as a result, another image with the same number of sub-images. So then we'll take the, let's say, 0, 0 coefficient from each block and find its variance. We'll take next the coefficient next to it, the same coefficient, location, all blocks, find its variance, and so on. Then we order the coefficients from largest variance here to smallest variance, as is clear from this plot. The idea is that the coefficients with the larger variance will contribute more towards the total energy of the image. So a transformation that decays faster is a more desirable one, in the sense that fewer coefficients represent a larger percentage of the energy in the image. So we compare here the so-called KL, or Karhunen-Loew transform, which results in statistically independent coefficients. However, the bases in this case are functions of the image, more specifically of the autocorrelation function of the image. We also show here the performance of the DCT, the discrete cosine transform, the Fourier transform, and the Hadamard transform. In comparing the Fourier and the transform and the discrete cosine transform, a clear distinguishing factor is that the Fourier transform coefficients are complex numbers, while the DCT coefficients are real numbers, and we much prefer working with real numbers than complex ones. So the DCT has this distinct advantage over the Fourier transform, but more than that, the DCT is the transformation of choice, is used in many of the image and video compression standards. Summarizing what I already said in the previous slide, the KL transform results in statistically independent transform coefficients. However, the main disadvantage is that the basis functions of KLT are a function of the image that needs to be encoded. The DCT is the transformation of choice. It's close to KLT for typical images, and actually there are theoretical results that show that for a specific model for the image, DCT and KLT coincide. The basis functions of cosines, are independent of the image, therefore do not need to be transmitted to the decoder. Since it's widely used in standards such as JPEG, the family of H.26 standards, video compression standards, and the family of MPEG standards, there are also efficient implementations of the DCT, embedded implementations, or even dedicated chips to perform the discrete cosine transform. Before we proceed, let's establish some notation. Assume we have two n by n matrices, and here for this segment they're denoted like this. So it's a matrix phi and the matrix gamma. So their inner product is formed by multiplying the corresponding elements one by one. So I'll multiply this times this element, and then this times this, and then this times this, and I will add them up. So the dot or inner product is clearly a scalar. Since in general I deal with complex matrices, then here I take the complex conjugate of each and every element of this second matrix. Then if I have a family of matrices, they're parametrized by U and V here. These matrices, they're orthonormal if when I take the inner product, it's equal to 0 when U is different than R and V is different than S, and it's equal to 1 when U equals R and V equals S. So the inner product of a matrix from this family of matrices with itself is 1. That's where the normal, orthonormal parts comes from. And the inner product of one matrix with any other matrix in the family is equal to 0. Given a family of orthonormal matrices, phi uv, that we just defined in the previous slide, then given any image f, it can be decomposed in terms of these bases, these orthonormal matrices. So I can write f as shown here. So this means that the image f is a coefficient here, f of 0, 0 times phi 0, 0, which is a matrix, plus f of 0, 1, and then the phi 0, 1, and so on, all the way to f n minus 1, n minus 1, phi n minus 1, n minus 1. So it's the weighted sum, where these are the weights here, the f's, of the basis function, these orthonormal matrices. How does one find the coefficients here, f of uv? We have to perform the projection of the image f onto each and every of these bases phi. And this projection, this inner product we defined, will give rise to this coefficient. We have seen this decomposition before with vectors, not matrices. So we're all familiar with the fact that if I have here an orthonormal basis, so this is vector E1, E2, and given a vector x, then I project x onto here. Let's say this is alpha 1, and this is alpha 2, and we simply say that vector x equals alpha 1 vector E1. I can put bars here to denote that these are vectors, plus alpha 2 vector E2. So this is the extension of this decomposition that I assume you're familiar with when now we have matrices and not vectors as bases. Here's a toy example. We have this image of a smiley face, and as basis we use Hadamard basis. I'll say a few more things later on. By projecting this image of the smiley face into each and every of these bases, we obtain these resulting coefficients. Only 4 of those are shown, and therefore, again, I can decompose this image as the weighted sum of these bases functions, and these are the corresponding weights. So the main idea is that if these bases are known, they're Hadamard bases to both encoder and decoder, all I need to send to the decoder are these projection coefficients, and the decoder, utilizing these coefficients, can reconstruct the image just using this expression shown here. I want to mention here the KL transformation for completeness. Our objective is to find a family of orthonormal bases, I call them phi uv, so that the resulting coefficients, capital FUV, that are obtained by projecting the image onto these orthonormal bases are uncorrelated. So according to the KL theorem, if I have such an image f of mn, and Rmn Pu Pq is its autocorrelation function, then I can find this family of orthonormal matrices that will result in uncorrelated coefficients by solving this equation. What this equation tells us is that these orthonormal bases are the eigenfunctions of the autocorrelation function. And this delta uv, it's simply the expected value of the magnitude of the coefficient, the magnitude of the coefficient squared. So we have a specific procedure in obtaining these orthonormal matrices we are after. However, they depend on the autocorrelation of the image, And although I can compute these phi's at the encoder, the decoder has no way of performing the same computation, and therefore these phi UVs need to be sent to the decoder. So it is a mathematically optimal transform for our purposes. However, is not practical one, because if I have to send the basis, this defeats the purpose of compression. In the class I teach here at Northwestern, I prove all these relationships. However, they're clearly beyond the scope of this particular class. We see here the 64 8x8 basis functions of the discrete cosine transform. Here is the interpretation of the colors. So in this first row, we have a one-dimensional cosine that increases in frequency horizontally. So vertically here it's constant. And in this column, we have a one-dimensional cosine that increases in frequency vertically. For the rest of the bases, we have a two-dimensional cosine whose frequency increases both horizontally and vertically, and down here is the basis with the highest frequency in 2 dimensions. I showed exactly this same plot back in week 2 when we talked about complex exponential signals, and I did make the comment at that point that we'll be encountering these basis functions when we talk about compression, and now is the time to do so. So, as I have explained already, given an 8x8 image block or image patch, we just find its projection to all these 64 bases. And if, for example, I find the projection or the inner product between this base and the 8x8 patch, a number will result, which we denoted by FUV, and this is the DCT coefficient. Clearly, the projection of the patch into this here basis, it's black, so all its values are equal to 1, will give us the sum of the intensities here. If I divide by 64, will give us the average value of the patch. So instead of having 64 intensity values here, I have 64 such coefficients. These, by the way, are real when we talk about the DCT transform. The advantage of working with the FUVs instead of the FMN, as we denoted earlier, is that now if somebody asks us to keep, let's say, 15% of the pixel values which are more important, we have no way of knowing which 15% of these 64 pixel values are more important than others. However, when we look at the DCT coefficients, is rather straightforward to keep the 15% of the 64 that have the largest values. These coefficients, again, are in principle uncorrelated, and therefore keeping the ones with the largest value, we will do a very good job in representing the original patch and also in preserving most of the energy in the original patch. Here we show the 64 8x8 Hadamard basis functions. Here's the interpretation of the colors, only 2 values, plus and minus 1. So it's a similar description as with DCT. I should mention that in both cases these bases are orthonormal. So in other words, the inner product of this with this is 0, this with any other is 0, but with itself is equal to 1 if it's normalized appropriately. So the story is the same. Given an 8x8 image patch, I can find the projections onto these bases, and these are the Hadamard transfer coefficients, which again are less correlated than the original image and therefore can serve our purposes for compressing the image. In order to demonstrate experimentally the effectiveness, the power of this decorrelating property of the transformations, we conduct here a very simple experiment. Given this image, we are asked to break it into 8x8 blocks, and then out of each of these blocks we are allowed to keep only 8 pixels or 8 coefficients, and we're supposed to throw the rest of them away. So trying to decide in the spatial domain here which 8 out of 64 coefficients are more important is very difficult. I have no means of doing it. However, if we go to the frequency domain, we can keep per block the 8 largest coefficients, and if we do so by defining a threshold and keeping only 8 out of the 64 per block that are above the threshold, right? We adjust the threshold so only 8 are above the threshold. Here is the reconstructed image. So we keep 8 and set the rest equal to 0. We see here that this is very close to the original one. We do the same experiment where now the location of the 8 coefficients are based on this zonal description. So if this is an 8 by 8 block in the discrete cosine domain, then we keep the 8 coefficients that are closest to the DC, so the 8 low frequency coefficients. Clearly, thresholding by and large should give better results than the zonal approximation, simply because there might be a large value coefficient down here, larger than any of the ones that I kept here that I have neglected. However, when thresholding is used, I have, in addition to the coefficients, transmit their location, so spend bits for the location, while this location information is fixed here when the zonal approximation is used. So if I look at the difference between the original and the encoded versions, here is their difference scaled appropriately. And what you can see is that the difference is really large at the edges, because the edges represent high frequency information, which was discarded in this particular case. We conduct the same experiment where now only 4 coefficients out of 64 are kept, and here's the result of thresholding, zonal. In this case, the same comments can be made as before, but I believe it's clearer here that the zonal approximation results in a larger error if we look at the intensity image or at the error than the method using thresholding. And again, it's the same experiment where now only 2 out of 64 coefficients are kept, and I believe it's quite impressive that even though 2 out of 64 coefficients are kept, still we obtain reconstructions here that convey quite a lot of the information about the original image. You start seeing these blocking artifacts clearly, but nevertheless, these, again, images are conveying quite a bit of information about the original image, and here I believe the error is much more pronounced with the zonal approximation than when using thresholding. So this is the basic idea behind transform-based encoding, and as we'll see next when we discuss JPEG, these are exactly the steps taken by JPEG or any transform-based encoding scheme by and large. The difference is how to perform quantization, how to decide which coefficients to keep and which to throw away, but more specifically, how to decide how to encode each and every coefficient with a fine or a coarse quantizer. Here, these are simple ideas to just demonstrate the effectiveness of decorrelation, but again, where the innovation and the novelty comes in is in the way, as we'll see, of quantizing as well as entropy encoding these resulting DCT coefficients.